We're going to introduce a new function today. It's called the modulus function, and it is deceptively simple. It seems really basic, and yet the kind of results we can get when we start combining it with other things are surprisingly complex. To begin with, though, we want to get into the habit of confidently and easily sketching common sorts of graphs. So here we've got a quadratic, a cubic, a reciprocal graph, an exponential, a log graph, and a trig graph. So if you can pause and have a go at making a quick sketch for each of these. They don't have to be particularly pretty, but they need to include the key features of the graph, the general shape, if there are any asymptotes, if there are any crossing points with either of the coordinate axes, to include that information. When you're done and you're ready to check your answers, continue the video. So our first one here, y equals x squared minus 4, there are a couple of different ways you might have approached this. You might start by factorizing the right-hand side. It's a difference of two squares, so we get x plus 2 in one bracket and x minus 2 in the other bracket. And that helps us to more easily see the roots of the equation. In other words, in this context, the points where the quadratic curve cuts the x-axis at 2 and at negative 2. We can also see directly by making x equal to 0 that it cuts the y-axis when y equals negative 4. From that information and the fact that we can already see it's a positive quadratic, we should be able to confidently sketch the curve. It looks something like this. Another nice way to look at this is as a straightforward graph transformation from y equals x squared. If you can get into the habit of looking at them like this, that can save you a lot of time. Y equals x squared we already know, and if we subtract 4, it means all of the points on this graph are 4 units lower down than the graph of y equals x squared. Every y coordinate is 4 below where it would have been on y equals x squared. So instead of crossing at 0, 0, it crosses at 0, negative 4, for instance. To identify exactly where it crosses the x-axis, you would still need to solve the equation, but you can do that either through factorizing or just simple rearranging. Graphs cross the x-axis when y equals 0, so we set y equal to 0, we rearrange and we solve. That same technique can be used in the second one, the cubic equation there. In general, cubics are not easy to factorize, so it's not always going to be possible to quickly and easily identify where a cubic crosses the x-axis. But in this case, well, we kind of get one result for free. If we ask what happens when x is 0, we get y equals 0. In other words, when y is 0, x is 0. So it crosses at the origin, and that gives us one of our x-axis crossing points. The factor theorem tells us that if we have a root, then we can create a factor from that root. So if there's a root of 2, there's a factor of x minus 2. In this case, we've got a root of 0, so we have a factor of x minus 0, or just x. Now, if you look at it, you can see x is a common factor of both terms. We can pull out x and have x multiplied by a bracket containing x squared minus 1. And then that bracket itself can be factorized. It's a difference of two squares. We'd have x plus 1 times x minus 1. And that means we have a graph that crosses at 0, 1, and negative 1 on the x-axis. The only place it crosses the y-axis is at the origin. But because it's a positive cubic, we already know that it comes from negative infinity and goes towards positive infinity as we move from left to right. In other words, if x is enormous, then y will also be enormous. If x is a huge negative, y will also be a huge negative. Remember, with an odd power, the sign is preserved. Unlike with x squared, where you square a large positive or negative number, you just get a large positive number. With x cubed, you get a large number of the same sign as the original. Y equals 1 over x. This is the first one of our graphs that has an asymptote. In fact, it has two. We can see one of the asymptotes by asking, when does this function not work? When will it break? And hopefully it's clear to see that if x is 0, then we can't calculate y. We'd be doing 1 over 0. So there's a problem when x equals 0. Well, x equals 0 is a vertical line, so we have a vertical asymptote. The y-axis itself is an asymptote for this curve. We can also figure out what happens in the long run. This is sometimes called the long-term behavior of a function. What happens as x gets bigger and bigger and bigger? Well, with x squared or x cubed, the answer is, well, y gets bigger and bigger and bigger. But with 1 over x, if x is enormous, 1 over x is tiny, and the bigger x gets, the smaller 1 over x gets. This also works for negative values of x. 1 over negative a billion is negative a billionth. So we have a function which is getting closer and closer to a y value of 0 as x increases without limit or decreases without limit. And that means we also have a horizontal asymptote, the x-axis itself, y equals 0. Once we've got that, and we think about the sign of our answer, when we do 1 over a positive number, we get a positive number. 1 over a negative, we get a negative. We should be able to see that we're looking at this particular curve. The next curve is an exponential curve. Doesn't really make a difference if we're thinking of y equals 2 to the x or y equals 10 to the x here. Just happens to be y equals e to the x, and they all have a very similar shape. They all cross the y-axis at 0, 1, because when x is 0, we have e to the 0, or 2 to the 0, or 10 to the 0, and any number to the power of 0 gives an answer of 1. So they all cross the y-axis at 0, 1. And also, although they get very, very big as x increases, they get very, very small as x becomes more and more negative. So we're expecting an asymptote for this one as well, and we get the classic exponential growth graph. Y equals ln x is the inverse function that goes along with y equals e to the x. What that means is it does the opposite. So while e to the x will take a fairly modest number, like say 10, and turn it into something enormous like 22,026, ln x does the opposite. You would have to give it a number as big as 22,026 for it to give you an answer that was a size 10. The other thing that we'll see with this one is that the graph is a reflection in some sense of the e to the x graph. And that's precisely because y equals ln x is equivalent to x equals e to the y. So in some sense it's the same as the previous graph, but with x and y swapped around. That's like swapping the x and y axes, which you can do if you pick up the paper and reflect it in the diagonal y equals x. We get this sort of curve. And as the exponential curve increases faster and faster, the logarithmic curve increases slower and slower. It's a reflection, so the steeper e to the x gets, the less steep ln x gets. And you can try this yourself on the calculator. If you do ln of a really, really big number, you'll find no matter how big a number you put in, the result is still pretty modest. And on the flip side, even if you put a fairly small number into e to the power of x, try e to the power of 20 or e to the power of 50, you will find an impossibly large number comes out the other side. We also have an asymptote for y equals ln x. The asymptote is the vertical line of the y-axis, x equals 0. Just like for e to the x, the asymptote is the horizontal line of the x-axis, y equals 0. And just like e to the x crosses the y-axis at 0, 1, ln x crosses the x-axis at 1, 0. The final curve is one of the trig functions, the sine wave. This curve starts at 0 because sine of 0 is 0. And if you ever have a bit of a mind blank, the calculator will help you out with that one. And then it starts by going up and then comes down. And it takes 360 degrees to do a complete cycle. So the up and down followed by continuing to go down until it gets to its lowest point, and then it comes back up again to 0 and then repeats. So here I've shown the 180 degrees that comes before the origin, followed by 360 degrees and then a bit more after the origin. You can get a sense of this curve. It goes on forever in both directions. Often we only interest ourselves in solutions between 0 and 360 degrees, but that's not necessarily always going to be the case. An extra question you might want to ask yourself before you move on is, how many of these functions could you identify the coordinates of the turning point for? And if you're wondering if you've got the skills to do that at this point, I can reassure you that provided you know your year 1 A-level maths, you can find the coordinates of any of the turning points of these curves. If it has a turning point, you can find the turning point. Now I'm going to give you some clues, and I'm going to see if you can think up a suitably straightforward function that will do what you can see this function doing. I'll give you an input value of 5, and the output value that corresponds to that is 11. You can't tell very much from just a single data point, so I'll give you another one or two. If the input is 4, the output will be 9. Well, now, if you're thinking mathematically, you might have come up with some kind of basic rule that fits these two data points, and you're going to wait and see if it fits the next one. The input is 2, the output is 5. Well, with 3 data points, you should be able to tell at the very least whether you're dealing with a straight line or a curve, and when you think you've got a rule that works, you can test it out with this 4th data point. 0 gives an output of 1. So if we were sketching this on a graph, we could have y equals f of x. So our coordinates will be the points 5, 11, 4, 9, 2, 5, and 0, 1. If you actually plot those points, you do get something that looks a lot like a straight line. The points are actually all in a dead straight line with one another, and so our rule seems to be a pretty good one. Until now. If you put a value of -3 into my rule, I get an answer out of 5. You were probably expecting it to be -5, but I got a 5. And the same with this one. In fact, we seem to be getting the same result from this for -6 as we previously got for +5. So something weird is happening. It almost looks like the function goes down and then comes back up again as we move to the left, like a quadratic graph. And yet, clearly it's not curved because we've already seen there were 4 points that all lay on a dead straight line. In fact, it almost looks like there's one rule for negative numbers and one rule for positive numbers. That's not quite what's happening here, but it's very close. Sometimes the numbers follow the rule shown by the black line with the positive gradient, and sometimes they follow the rule described by the red line with a negative gradient. So, for instance, with -3, perhaps we are multiplying by -2 and then taking away 1. Whereas with +4, we multiplied by 2 and we added 1. So we've got one line that has an equation y equals 2x plus 1, and another line that seems to have equation y equals -2x minus 1. Well, it's a very similar function. It's exactly the same, apart from the fact that we've multiplied the entire thing by -1. We've changed the sign of the whole thing. We're going to look now at what kind of function we can define that does this for us, and we'll see what kind of impact that has. This essentially is the bit that we're interested in. We don't want those bits that go below the x-axis. The outputs that you saw in that column for f of x are all non-negative. If we'd put in a number like -1/2 and followed my rule, then we would have got an answer of 0. So we can get zeros out of this function, we just can't ever get a negative result. And it gives us this strange spiky graph, which seems to break the implicit rules of functions that you've grown used to using. A function should follow the same rule all the way across. That's the way we've treated them in the past, but that's not necessarily the way they have to be defined. On the contrary, a function just has to be a rule or set of rules that provides a single unique output for any valid input. In other words, there is an answer. If you give me an input within the range for which your function is defined, there will be an output that you can give me, one single output that corresponds to the input I put in. Now, it doesn't necessarily have to be a different output to what I might get if I put a different number in, but it does need to be a single valid result that comes out. But there's no rule that says I have to apply the same rule to different input values. We can be as flexible as we like with this. This particular one's quite nice. If you want to try pausing and sketching the curve y equals -x minus 4 times x plus 4, just for x values between 0 and 4, and then sketch the other quadratic, -x minus 4 times x minus 8, but sketch that one between values of x between 4 and 8, you'll see that those two curves actually happen to meet up at the joining point. And they're not the same curve at all, but perhaps they would do a decent job of modeling some kind of mechanical situation. Somebody drops a bouncy ball and it goes bouncing and rolling away. Now, the quadratics involved are different quadratics, but effectively they're describing one single situation. And sometimes that is the simplest way. You will probably need a different equation to describe the phase of motion for a free fall parachutist while he's in free fall compared to while he's got a parachute out and in free fall compared to when he's landing. They're all different phases of motion. If you've got a car which is accelerating or in first gear or in second gear, the motion is going to look different because of the different way the engine's working. So it might well be that you need a different rule to describe each phase of the motion. This is often referred to as a piecewise function. It's defined in pieces, so each individual piece has its own unique rule. And that is how we're going to define the modulus function. It is a piecewise function which has a different rule depending on the input. You can apply it to all sorts, but we're going to start just with the simplest version, mod x, where the input is just the number x and the output is either the same as the input or the input with its sign changed. Now the way we apply that mathematically is just to multiply by -1. So the output is either going to be exactly the same as the number that went in, or we change its sign by putting a minus in front and it gives us a number which has the opposite sign. But crucially, it only does this when we're dealing with a negative input. So if I give you a number like 7 and you apply this function, you give me an answer of 7. If I give you 14, you give me an answer of 14. If I give you a number of -3, then you recognize that this is the second category of input. It's a negative input, which means you have to apply your change of sign rule. And when you do that, the -3 becomes -3, which is 3. So I never get a negative result out of the other side of this function. And it looks like this. This weird bouncy graph is part y equals x and part y equals -x. Whenever x is positive, we get this bit of the graph. And whenever x is negative, we get this bit of the graph. So for negative values, we're basically doing the negative of y equals x. And for positive values, we're just doing y equals x. And we can describe both of them in one convenient shorthand. These two vertical lines either side of your input tell us that we're going to take whatever that thing is inside there. Think of them a bit like brackets, but brackets that have a special job. These brackets don't just contain the stuff inside, but they positivize it. In other words, if it's not yet positive, they make it positive by changing the sign. But if it already is positive, they don't do anything to it. This is different to just putting a minus sign in front of a bracket, because that will always change the sign of the input. If you throw something negative into a bracket that's got a minus sign outside, then it turns that negative thing into a positive number. This function will only change the sign if it needs to make it positive. You can think of it like a flow diagram. You get your input. Is it negative? No. Okay, then do nothing at all. You just leave it as is. If it is negative, you change the sign. And as a result, all that ever comes out are positive values. And that's why this graph that we've got on the screen only ever gives positive values for y. The output value is always positive or 0. 0 is the only exception. So essentially, we're getting a non-negative output. And the graph is forced to have no values below the x-axis if it is modulus of something. Next, we'll try an example with something a little more in it than just mod x. This one is y equals mod 2x minus 3. And it might be worth just trying a few numbers in this to get an intuition for what's going on. If we try 2 times 10 take away 3, we'll get 17, and then the modulus function gets applied to 17, and it has a result of 17. The modulus function doesn't change anything if what it's acting on is already a positive value. But what if x was a bit smaller? Maybe x is minus 100, then we have 2 times minus 100 and take away 3. That gives us negative 203, and the modulus function will come into play at that point. I've given it an input of minus 203, so the modulus function takes that input, changes the sign, and spits out the other side, positive 203. But now you could ask the question, when does it change? Because for some values of x, the result inside that modulus signs will be positive already, and for other values it'll be negative and need changing. Well, the cutoff point between positive and negative is at 0. So the quickest way to see that is to ask yourself when 2x minus 3 is equal to 0. For what value of x does that happen? Well, if 2x minus 3 is 0, then 2x is 3, therefore x is 3 over 2, or 1.5. If you try a number smaller than 1.5, like 1, you'll get a negative number inside the modulus signs. Modulus of negative 1 in that case. 2 times 1 take away 3 is minus 1. And then the modulus function will have to change the sign of that to give a result of 1. Whereas if you put in a number bigger than 1.5, like say 2, 2 times 2 take away 3 is positive 1, so the modulus function doesn't need to change anything. So we can get a sense of this function, the fact that it maintains the same behavior as y equals 2x minus 3 when x is big enough. And by big enough, we mean if x is at least 1.5. But if x is below 1.5, then this function effectively does the job of y equals minus, in a bracket, 2x minus 3. It changes the sign of everything inside those modulus signs. So this is how we look at it. We say when the stuff inside is at least 0, then it'll be exactly the same as if we didn't have the modulus signs at all. And when the stuff inside is negative, then it'll be exactly the same as if we had a bracket and a minus sign in front. And that allows us to actually solve equations and sketch graphs, because we're taking our new function notation and just breaking it apart into where it comes from, what it's built from. And it's not a crazy, wacky, mysterious function like sin x or ln x that does something weird and it helps to have a calculator to evaluate. It's either doing nothing at all or it's changing the sign. The subtlety comes into the fact that we need to figure out when it does which of those two things. But the things it does are actually pretty straightforward. Now, if it's sometimes the same as 2x minus 3 and sometimes the same as minus 2x minus 3, then it makes sense to start with those curves, or those straight lines in this case, when we're trying to figure out the graph of this modulus function. In general, what we do is we figure out the values of x for which the function is unchanged, and the values for x for which it will be reflected in the x-axis. You'll see what this means in a moment, but if the function is reflected in the x-axis, that's equivalent to sticking a minus sign in front of the whole thing. Positive values would end up being negative if you put a minus sign in front. In our case, we're actually just putting a minus sign in front of something which is already negative, which reflects it above the x-axis. So here is the line y equals 2x minus 3. And if we also sketch on the negative, y equals minus 2x minus 3, you can see that both lines cross at the x-axis, for instance. In fact, they happen to cross when x equals 1.5. That's when 2x minus 3 is 0. So the negative and the positive give the same result. Now the modulus function is the same as y equals 2x minus 3 whenever x is at least as big as 3 over 2. That means for x values that are to the right of 1.5, we're going to be following this graph. And then if x values are to the left of 3 over 2, we're going to be following the other graph. So we'll be doing this one. We'll be up there, which means this is our modulus function. It's the positive bits, if you like. Looks like this V-shaped graph, and it follows the positive 2x minus 3 straight line while that is above the x-axis. And as soon as it isn't anymore, it basically gives us the reflection. Negative of 2x minus 3 is a perfect reflection of y equals 2x minus 3 in the x-axis. So we can think of it as being a little bit like putting a mirror down on the x-axis, and a ray of light comes flying in from the top right following y equals 2x minus 3, hits the mirror and bounces off, and now it follows the reflected beam, which is the red dotted line, negative 2x minus 3. This is therefore the modulus function. This is the one that is represented by mod 2x minus 3. For part of its length, it is the same as y equals 2x minus 3, and for the other part is the same as y equals negative 2x minus 3. Now the next bit of the question asks about solving an equation, hence solve 2x minus 3 equals x. So I've drawn on our graph the line y equals x. You remember, if you were trying to solve an equation that looks something like this, a good approach is to ask ourselves, where does the graph of y equals the left-hand side cross the graph of y equals the right-hand side? Because when they cross, it'll mean they have the same y value for the same x value, and that's equivalent to finding the x value that corresponds to the solution to the equation. So really what we're saying is, where does the big blue graph of mod 2x minus 3 cross the new black graph y equals x? And hopefully you can see that there's a couple of places where that happens. But how do we find the exact values? It's not enough on a graph to look at it and say, oh, it's somewhere between 2 and 4, so maybe it's 3, maybe it's 3.2. Oh, there's one between 0 and 2, so I'm going to guess 1.5. What we need to do is find a rigorous way of finding the exact values. Luckily, though, we can use exactly what we did to sketch it. We can break the modulus function apart into two separate cases. Either it's the same as 2x minus 3, in which case we're just solving 2x minus 3 equals x, and we get a result straight away, x equals 3. Or it's the same as minus 2x minus 3, and we can try that one as well. And that is also easy to solve. Take care with your negatives, rearrange, and you'll get x equals 1. And it's a good idea to test those. I would recommend, as always, test them back in the original equation. We can do 2 lots of 3, take away 3, and see if it's the same as 3. It is. We can do 2 lots of 1, take away 3, do the modulus of it, and see if that's the same as 1. So it seems to work. And in fact, you can see that they fit where they should have been on the graph. You should now be able to have a go at a few questions from exercise 2a. Make sure you check that your solutions fit in the original equation and think carefully about what the modulus function does for you. If you want a bit of a bonus question, can you see why there aren't any solutions to mod 2x minus 3 equals negative x? Maybe try drawing the graph y equals minus x on the same set of axes. And then see if you can answer this question. How many solutions are there to mod 2x minus 3 equals 3x? Be a little bit careful with which bits of the curves of the graphs the new straight line we're drawing crosses. Now we're going to mix it up a bit and have a look at something which isn't a straight line at all. This one's a quadratic, y equals mod x squared minus 4. And I want you to pause the video and have a think about what you think this will look like. Try sketching it. When you're ready, unpause and we'll work through it together. So here's the original graph. If we ignore the modulus signs, we just get y equals x squared minus 4. We had this one earlier in the session when you had to sketch it near the beginning. It crosses the x-axis at 2 and at minus 2, crosses the y-axis at minus 4, and we get this classic parabolic shape. But then, because the mod graph is sometimes the same as not doing anything, and sometimes the same as doing the negative, I'm also going to sketch the negative one. If we chuck them on the same set of axes, you can see that they both cross the x-axis at the same places, but the negative x squared minus 4 graph crosses the y-axis of positive 4 instead of negative 4. Now, if we want the modulus function here, it needs to follow the positive quadratic only when the positive quadratic gives positive results. And it switches allegiance as soon as that stops happening, and it starts to follow the negative quadratic whenever the positive quadratic isn't giving it positive results anymore. So it will happily follow the positive quadratic down all the way along here. Everything's fine. But as soon as it gets to here, it finds if it continues to follow the positive quadratic, we'd get negative results. Those negative results get automatically converted to positive results. In other words, we are now changing the sign. So the modulus function has to actively change the sign for x values between minus 2 and 2. Then when it gets up to 2 again, it has to stop changing the sign because the result, x squared minus 4, will be big enough, higher than 0 in other words, that it can continue just following the ordinary positive version, y equals x squared minus 4. So this is the graph of y equals mod x squared minus 4. Very weird looking shape. You can imagine if you can start applying this function to all sorts of curves, you can get all sorts of weird results. The gradient switches just like that. When you get to x equals minus 2 or x equals 2, the gradient immediately changes from being a steep negative to steep positive or vice versa. So some things break down at the edges when you have a piecewise function like this, but everything else you know about the curves, they're basically built from either the black dotted line or the red dotted line. And it just depends what your x values are, which of those two you have to work with at any given moment. So just to give you an idea of what's coming up later, if we had a straight line crossing our modulus graph here, potentially you could have 4 different solutions. Where does y equals 2 cross y equals mod x squared minus 4, for instance? That would just be a nice simple horizontal line. And you can see 4 different solutions. If you decide to change your y value, or you have a different line completely, maybe it only has 1 solution. Maybe it has no solutions at all. Maybe it's a line that does this. Maybe it has 2 solutions, one of them corresponding to the positive branch of the quadratic and one corresponding to the negative bit of the quadratic. There are all sorts of possibilities, so it can get quite complicated if you don't have a graph to look at, because you can't necessarily see which branch of the graph you're interested in. Now, I want you to get a feel for how the modulus function works with all sorts of curves. So we're going to go back to the graphs that we saw before. This one is one that we've recently done an example of, so that should be nice and quick for you. This one, look back at the original cubic you drew. You could maybe even draw your modulus graph on the same set of axes. We've got the modulus of 1 over x, the reciprocal graph. Then we have the exponential, the log, and the trig graphs. Pause the video, have a go at drawing the modulus version of those 6 curves you did at the beginning of the session. Then come back and see if your results match up with mine. All right, mod x squared minus 4 to start with. We've already seen this one. This is a less cluttered version without all the others going on behind the scenes. If you've got dotted lines in yours, that's not a problem. Just make it clear which one is your modulus function, particularly if it's in an exam question. It wants to be unambiguous and clear what you mean. For the cubic, looks very interesting. It suddenly becomes symmetrical. Cubic graphs have rotational symmetry about their point of inflection anyway. This particular cubic graph had its point of inflection at the origin. Now it's been reflected, it now has reflection symmetry. So the original cubic would have started low, had an up wobble between -1 and 0, and then a down wobble with a minimum between 0 and 1, and then continued up high. So the bits of this that are actually reflections are this bit and this bit. The original function would have had those bits below the axis. So they've ended up disappearing because it would have been something like this. Now the next one looks very similar. In fact, it might remind you of y equals 1 over x squared, because of course that's a similar sort of reciprocal shape, but the x squared forces the values to never be negative. In this case, we're keeping the size of 1 over x, but we're stopping any negative results. So 1 over minus 7 is now giving a positive 7th instead of a negative 7th. Y equals mod e to the x is the same as y equals e to the x, because e to the x is never negative anyway, so it doesn't ever need to change. ln, however, does go negative. ln is negative between 0 and 1, so we're going to need minus ln x between 0 and 1, and ln x from 1 upwards. We get this interesting shape. You can see the asymptote is still on the y-axis, but this time the curve shoots up towards the asymptote instead of down. And mod sin x might be the nicest one. The sin x graph wobbles above and below the x-axis forever. Now if we use the modulus of sin x, then all the wobbles that go below the x-axis get reflected above. So you know what the standard sine x graph would look like. After the up and down, it would continue down to a minimum at 270 degrees and then back up to 0 at 360. Now all the maximum points are the same, but all the minimum points have now been reflected up to become identical to the maximum points. Our next example is going to involve two modulus graphs, and we've got an inequality sign in there as well. So we're not just solving an equation, but we're having to identify a range of values for which this is true. Now, the best way to think of any inequality that isn't just a straightforward straight line inequality is to break it apart into sections, to think about the critical values, the points where the left-hand side and right-hand side are actually equal to each other, and then to investigate each region to find out whether the inequality holds at each point. It's the same method that we would use for a quadratic inequality. We don't just find the solutions 2 and 5 and then say, therefore x is between 2 and 5, or x is less than 2 and x is less than 5. We have to look at the graph and work out whether we need to be between 2 and 5, or perhaps below 2 or above 5. Generally, that'll be how it looks with a quadratic. This will be a similar sort of idea. The very first step that I would recommend for something like this is to draw the graph. So for mod 2x minus 1, we can draw that side, y equals mod 2x minus 1. Think of the graph y equals 2x minus 1, even sketch that graph if you like, but when it starts to go negative, sketch its reflection in the x-axis instead, which will be the line y equals minus 2x plus 1. Change the sign of the whole thing. Now for the other side, something important has happened. We have mod x and then plus 4. The plus 4 is not inside the rest of the function. And that means that the modulus bit, which makes sure what comes out is never negative, only acts on the x. And after it's done its job, then we add 4. Now this might remind you a little bit of completing the square, where if we have something squared add 4, we know for certain that the overall result can never go below 4. Because the something squared is never negative, and then you're adding 4. It's like having one bank account that can't ever go overdrawn, you can never go into debt, and then someone gives you £4. Worst case scenario, you've now got £4. And that will be if you have nothing in the bank. The only alternative to that is that you've got something in the bank and you have more than £4. But it's not possible to have less than 4 because your bank is not overdrawn. Now, the simplest way to draw this is probably by thinking of graph transformations. Y equals mod x is a graph you should be able to draw quickly and easily now. It's the same as y equals x on the right, and it's the same as y equals minus x on the left. So it's a nice 45-degree zigzag bounce. If we take that graph and we move it up 4 places, we've got the right-hand side of this inequality. So here we go. I've included the dotted lines for our construction lines as well. But you can see the blue graph corresponds to y equals mod 2x minus 1. And the black graph corresponds to y equals mod x plus 4. You can see the lines that built mod x plus 4 are y equals x plus 4 and y equals minus x plus 4. Because the 4 wasn't inside the modulus sign, it didn't have its sign changed at any point. You're always adding 4. You do it after you mess with the x using the modulus function. Now, if we want to know when the blue graph is at least as big as the black graph, then we can already see on the graph that's going to happen provided x is big enough. Looks like it happens at the far right. Certainly the blue graph is above the black graph, and also at the far left where the blue graph is above the black graph. But in order to identify precisely the regions, we are going to need to know where those graphs cross. So we start with this. 2x minus 1 is the positive version of mod 2x minus 1. In fact, this line here is y equals 2x minus 1. And then x plus 4 is the positive version of y equals mod x plus 4. So when we solve an equation involving modulus signs, we don't actually solve an equation with modulus signs in it. We break out the piecewise function that the modulus sign represents. We say either that mod x plus 4 is x add 4 or it's negative x add 4. It's one of those two things. The next one we look at is actually the negative version. So for each of those two modulus functions, there's a negative side as well as a positive side. It looks like the second crossing point that we're interested in is a crossing point between the negatives, just like the first crossing point was a crossing point between the positive sides. And again, once you've done that, it's a very simple equation to solve. It doesn't take a whole lot of hard work to get a value. Make sure your value looks sensible, because it's easy to mess up negative signs with these questions. But getting a value for x equals 5 looks plausible for this positive one, and a value of x equals negative 3, that also looks plausible for this negative one. The last thing here we would need to do is solve the inequality. These numbers are basically the critical values. They're the points where one graph overtakes another graph. If x is somewhere between negative 3 and 5, then the right-hand side of the graph wins. Mod x plus 4 is going to give you a bigger answer than mod 2x minus 1. But provided you go outside that range, then the left-hand side wins. 2x minus 1 will be the biggest. Mod 2x minus 1, I should say. So we can see that x needs to be either less than or equal to negative 3 or greater than or equal to positive 5. Provided that is the case, then you will definitely be in a region where the inequality holds, and there are no other regions where that's the case. One thing to watch out for here, we looked at the positive branch of both modulus graphs, and we looked at the negative branch of both, and that gave us two equations. But they're not the only two equations we could have formed. In fact, technically, there are 4 different options. We could have the left-hand side be the positive branch and the right-hand side positive, or the left positive and the right negative, or the left negative and the right positive, or the left negative and the right negative. So you've got 4 different options, and we've only looked at 2 of them. And there's no reason why you wouldn't necessarily need to look at these others in a different situation. The negative branch of one with the positive branch of another potentially might be the correct one to look at. But in this case, that doesn't work, because when we looked at our graph, we could see the positive branch of the mod 2x minus 1 graph does not cross the negative branch of the mod x plus 4 graph. They don't cross at all. The dotted lines from them may well cross, and that's why these two solutions appear. They're not valid solutions, they are phantom solutions. So the real solutions are these two, and we can see them on the graph. The phantom solutions are actually these two, where the dotted lines that correspond to the functions that the mod function is built from may cross each other. But unless the condition is met, it's a bit like saying, when is mod x equal to negative 4? Well, either when x is negative 4 or when minus x is negative 4. Well, the problem with that is x can only be negative 4 if mod x is equal to x, and mod x cannot be equal to x if x is negative. Mod x can never be equal to negative 4 because mod x is always a positive value. You should be able to have a go at the later questions from exercise 2a now. The last thing I want to do, if you're still watching, is just to compare a few different ways of using the modulus function within another function. I've got 2 alternatives here. We have y equals f of x, some cubic graph that you can see on the screen, and then we can either enclose the entire thing with modulus signs. So we say whatever output comes from this function, I want to change it to a positive number if it isn't one already. The alternative is to change the input to a positive number if it isn't one already before we apply the cubic function. So I'd encourage you to pause and have a think. See if you can come up with a graph for each of these 2 possibilities. It'll take a bit of thought. You might need to try plugging some numbers in. Remember, you can use the graph that's on the screen so that if your input is negative 1, then you can see the output will be 2, because we can follow it up there and see the result directly. Have a go, and when you want to be put out of your misery, come back and I will show you the 2 graphs. So here are our graphs. Maybe some of yours look a bit like this. The next question is which? One of them is going to be the modulus of the function. The other is going to be the function of the modulus of the input. Well, the easiest way to tell which is by looking at which function cannot ever be negative. And that has got to be this one here on the left. Because it's a modulus function wrapped around something. It doesn't matter what the something is, the modulus function only ever gives positive results. Whereas on the other side, we've got f of mod x. And what that really means is only positive numbers will go into the function f, but that doesn't necessarily mean that only positive numbers will come out. We know from looking at this graph here, if you put a number like 0.7 into the curve, you'll get a negative result. So there must be some negative values you can get. Now there's some interesting symmetry in that blue one. Let's look at the red one to start with. The red one in some sense preserves a lot of the features of the original green graph. The green graph has a maximum which is higher than 2, and the modulus f of x graph, the red one, has the same maximum point. The minimum that happens on the green graph, that goes down to something like negative 0.7, that has become a maximum that goes up to about 0.7, but it happens at the same point. What's really happened here is the graph of y equals f of x and the graph of y equals negative f of x have been used interchangeably depending on what the modulus function needs to make sure it has a positive output everywhere. So anytime f of x dips below the x-axis, we get a bounce, and the function will reflect the bits that are below the axis and not the bits that are above. They stay put. Now f of mod x is quite a hard one to get your head around. This one, the blue one, f of mod x, is essentially calculating things like f of 1, f of 2, f of 3 when you put numbers like 1, 2 and 3 in, which is why it looks exactly the same as y equals f of x. Because when you put in 1 and then change it to a positive number, it already is a positive number, so you'll get f of 1 when you put in 1. The difference happens when you try putting in negative numbers for x. So when we are trying to plot the bit of f of mod x, when x is, say, minus 2, we try putting minus 2 in, the minus 2 gets turned into a 2, and then the function gets applied to 2. And if you look up 2 on the green graph, you get quite a high number. It's going to be 5 point something maybe. So that's exactly what the blue graph will plot at negative 2. In fact, it plots the same thing at negative 2 as it plots at 2, because in both cases, it's evaluating f of 2. So we get this symmetry in the y-axis. Exactly the same thing happens on the left as happens on the right. And we lose all the information about what the original function did for negative values of x. Because whenever we have a negative value of x, it gets cleaned up. It gets positivized. It loses a negative sign if it had one. And so the only values we ever put into our function f are positive values of x. And our graph doesn't display any information about what the function f will do with negative numbers. Here's a couple of other things to try. See if you can use this idea for yourself. It's a really good way to make sense of it, because if you're anything like me, you'll still be a little confused by this whole idea. It takes quite a while for it to sink in and make sense properly. The best way to do that is to sketch these for yourself. Y equals mod sine x will be similar to the red one on the left, and y equals sine of mod x will behave in a similar way to the blue one on the right. And if you've managed to draw both of those, see if you can figure out which input values x will make those two graphs the same. When are they showing the same thing? A good way of checking your results for this is to use GeoGebra. If you go to GeoGebra online or you download the app, you can use ABS for absolute value. Y equals ABS, open brackets, sine x, close brackets, and it will show you the graph that you're trying to draw. You can also use the pipe symbol, which is the vertical line character on your keyboard, but you'll find that GeoGebra recognizes what you mean if you use the absolute value function.